Can you get the definition yourself from this example? Because I have taken the minors of this element of this matrix. Can you come to the definition by taking this example?
I'm the largest determinant which is not zero. Whose determinant is not zero?
Yes, you are right. And in another way? We can say that
Order
R
of
will
the
be the rank.
largest.
Yes, say order of the.
Order of the largest submatrix whose determinant is non-zero.
Yes, order of the largest submatrix. What do you, yes, repeat again, order of?
Order of the largest submatrix whose determinant is non-zero.
Yes, that is also correct. Another definition, can you say?
Largest square matrix inside a matrix whose determinant is non-zero.
Okay, another definition, what you can say? When I started this,
highest order of non-singular matrix.
Highest order of non-singular matrix. That is not a proper thing. That is not a proper.
Or submatrix.
Okay, I'm telling R will be called the rank of the matrix if you get a submatrix or the minor of the matrix whose determinant is not zero, but there will be other matrix of or the higher order than R. That means more than R. Okay, whose determinant will be zero. Like over here, R over here the rank of the matrix. So if we take the minor of this, R will be the rank of the matrix if the minor of this matrix is not equal to zero, but there are other minors which are greater than R whose determinant is zero. And in another way, what you can say, now when I started this taking the determinant, what I said over here, like one student have said that this is the multiple of this, means they are the same element. So second row is the multiple of first row, 2 times multiple. That means they are dependent. Can you get it?
Yes, ma'am.
So this second row is dependent on the first row. How? Because this is 2 times of the first row. So from here also you can get the rank of the matrix. So R will be called, so we can get the rank R as the number of linearly independent rows or column that occurs in the matrix. But the point, because see, if we are dependent, what will happen? Obviously, the matrix will be turned to determinant zero. When it is tending to determinant zero, that means the rank of the matrix cannot be equal to the order that we have considered, order of the matrix, which gave zero determinant, because they were linearly dependent. Can you follow? Now, if we take the submatrix over here, now this is not linearly dependent. See over here, neither row-wise it is dependent, nor column-wise it is dependent. So that is why you are getting the rank as 2. So this is another alternative way. So the first method by which we are taking the minor and then checking the rank, that is actually a very time-taking task, because if you have a very big matrix, 4x4 matrix, and then take the determinant and sub-minors, because the number of minors will be increasing. This is not just this you have got only by taking the one minor for the 3x3 matrix. You can also get this as another minor. Again, you can get this as another minor. So you will get many minors over here. Isn't it? Like if this is 0, then there may be another minor which may not be equal to 0. So this will be a time-consuming task to check the rank of the matrix. The simplest method is that you can check whether the number of rows or column are linearly independent or dependent. And the most simplest one is by converting the matrix to a echelon form. And actually by applying the transformation to the matrix. Okay, now the rank of the matrix definition, you can get it over here in the book. See, rank of the matrix. A matrix is said to be of rank R if it has at least one non-singular submatrix. Non-singular matrix means What is the meaning of non-singular matrix? Whose determinant is not. Yes.
Determinant is not equal
Yes.
to 0.
If the determinant is not equal to 0, like I was doing in the example, whose determinant is not equal to 0, then of the submatrix of order R, but has no non-singular matrix of order more than R. That means you will get some matrix whose order is greater than R, but the determinant value is what will be the value?
0.
Yes, the determinant value is 0. So same thing I was explaining earlier. So if you ask for the definition anywhere, so it is not necessary that you have to mug up this sentence. Okay, by just understanding the example, you can remember what is rank of the matrix. And the alternative way also I have said that when you get a determinant 0, when the elements of the matrix either in row or in column, if they are linearly dependent. So you have to have the independent rows and columns. So if the number of independent rows or columns, suppose if it is 3, then the rank of the matrix will be 3. Got it? Now let us take one example over here. There are some properties on rank also. Like if we have all the elements in the matrix are 0, then what will be the rank? What will be the rank?
Ma'am, please pardon.
0.
If all the elements of the matrix is 0, what will be the rank?
0.
1.
Yes, because whatever minus you get, the values keep on moving to 0 only. And if you take the determinant of the big matrix also, you will have a 0 value. So you cannot get a matrix which is non-zero. And if suppose you have a matrix of order, if A is a matrix of order n, and this matrix is non-singular. Non-singular means the determinant value is not equal to 0. So what will be the rank of this matrix? Looking at this example?
N.
3.
Yes. Yeah, means n over here. When I'm considering n, it is n.
Ma'am, then
And
if
what will
all the 3 rows are same, then the rank is 1.
Yes. So by row transformation, you can come to the easiest way of finding the rank. So when you do the row transformation, you will either get a lower triangular matrix or the upper triangular matrix. Like if you have row transformation means what? You can apply some calculations of either you interchange the row so that you can add or subtract some elements of the row, or interchange the column. When you interchange the row and column, that is just called the transformation of the matrix. When you interchange only row, then it is called the row transformation. When you apply the operation only on column, then it is called the column transformation of the matrix. So what you can do, you can either multiply any scalar quantity to this. Scalar, I think you can know what is scalar. Means any number, okay, any real number. Any number that you can multiply with the matrix and subtract it with the other element of the matrix so that you can convert it into a simplest form, the echelon form. Like echelon form, you can have some elements over here. And over here you are having 0, you are having over here. So this is actually the form of the matrix. This form of the matrix will be called as lower triangular matrix. Okay, where you have a non-zero elements of the row below the diagonal. So this is called the lower triangular. Or you can have another form of matrix like so this is another form of matrix where you have non-zero rows above the diagonal elements. So this is called the upper triangular matrix. So in this case, when it is a lower triangular or upper triangular matrix, so the rank of the matrix will be number of non-zero columns in the lower triangular matrix, or the number of non-zero rows in the upper triangular matrix. So number of non-zero rows or number of non-zero columns will determine the rank of the matrix. Okay, so when you are converting this matrix to a lower triangular or upper triangular matrix, so the number of non-zero rows or columns will define the rank of the matrix. Why? Can you say me why? Can anybody say that? Then why I am saying that the number of rows and number of columns, non-zero rows and columns will give the rank of the matrix?
Linearly independent.
Another answer. Okay, you can guess because the same answer lies in the previous definition which I have explained. Okay, you can think over it. Again, I will come back over here. And
And the minus will be 0, determinant of minus.
Yes, you're right. So he gave the answer. And now the other form that you can convert is to normal form. Normal is actually the identity matrix form. Like there will be some portion of the element which will have an identity matrix. Like identity matrix means 1, 1, 1, all the elements. So either you can have a normal form IR and there is some null matrix form over here. So this is called the normal form. So if R will be the rank of the matrix based on this rank of identity matrix because other elements are 0. So these forms you can reach to these forms by some transformation in the matrix. Transformation, like I can give you one example over here, like this example. You can consider this example. Like we can take the transformation row 2 element is equal to row 2 minus 2 times row 1. So this is also called a row transformation. Got it? So transformation means you add, you subtract, or you minus, or you interchange the rows and columns so that you can change the elements of the matrix in some form. So this is also a row transformation, like you can bring this above and this element you can bring it down. So that is also called a row transformation. Or you can bring this side, all the elements, but it should be done to all the elements of the column, not only one element. Okay, that will not be called as row transformation. If you do the transformation, it should be with all the elements of that particular row or column. So if you do the column transformation, then this will come this side, this will come this side, or you do any multiplication and whatever you want. So these are the simplest techniques by which you can find the rank. Don't go for finding the minus of the matrix. If it is a big matrix, don't go for finding the minus. It will be a wastage of time. So this is fine. Let us come to the example. Like you have this matrix. Now, what will be the rank of this matrix?
2.
Yes. How you got it?
Because, ma'am, you have said that this is 2 into 4 matrix and the smaller number is 2. That's why.
And again, you have to check one more condition. You can say that the rank of the matrix will be less than or equal to 2. You can have the minimum among these two, but again, you have to check.
Of the last 2 columns.
Yes, these are actually non-zero because if you take these elements, these are non-zero. Okay, like this into this minus this into, so you are having a determinant of this is non-zero. Any of the minus determinant that you take, it's non-zero. And another alternative way, what you can do, you cannot find any.
Both are linearly independent.
Yes, both are linearly independent. You cannot get any multiple combination with another row. So they are independent. Okay, now let us come to this matrix. Okay, now what will be the rank of this matrix? If you take the determinant and find the minor, it will be time consuming. You apply the row transformation. So when you do the row transformation, what you can do, see over here, you can just
rank would be 2,
3.
Row 1 plus row 2.
Yeah, you can either convert it into upper triangular, lower triangular, or to the normal form. So when you do the row, apply the transformation, in that process only you can guess what you are getting. Looking at this, you cannot guess what you will be getting. Okay, when you as you proceed it, then you can guess. Or forcefully you can bring to that form also by interchanging the rows and columns. Like sometimes we get the question like find the rank by reducing it to normal form, by reducing it to equivalent form or upper triangle or lower triangle. So forcefully you can do it by interchanging the rows and column and arrange it according to the definition. So over here, just you apply some elementary transformation. So you can take it row 2 as row 2 equal to row 2 minus row 1, and you can take row 3. You can apply multiple operation together. It is not that you just take one operation at a time. Like over here I am doing.
Ma'am, we can do just.
Yes.
Ma'am, when we can write row 1 equals to row 3 minus row 1, which will be equal to row 2.
Yes, that way also. Whichever way you find is simplest, so that the main target is to get some element 0. That is the main target. You will not have a unique transformation rule. But the result will be a unique. Whatever transformation you apply, you will get finally you will get a unique answer. So I have taken this transformation. Anybody can take any other transformation, just like the other one I said. Row 3 will be equal to row 3 minus row 1 plus row 2. So anyway, you can take.
Ma'am, could you explain that independent and the dependent part?
Okay, independent and dependent parts. Over here, see, if you look at these two, if you take a look at these two, are all the elements of this some combination of the first two element?
No, ma'am.
No, so they are like, see, I can say that a child is dependent on the parent. That means there is some relation.
Yes, ma'am.
Isn't it? So I can say that one row is dependent on the other row when there is some relation. Either it can be multiple of something or division of something, or if you add or subtract anything. So one row when it is dependent on another row means if you can find some relation between some rows or some columns, then they will be dependent. If you cannot find any relation, then you will say that it is independent. And it is obvious when there are some relation, then determinant value will obviously come to 0. So in that case, the rank cannot be equal to that that order at that particular stage. Okay, it will obviously be reduced to one lower than that current stage.
Okay.
So over here, these two are independent. Like if suppose this is 6, okay, and suppose this is 2, and this is, then you can say that this is 2 times this. So this is dependent on this previous element because this is a scalar 2 times scalar multiple of the previous row. So now you say what is the rank?
2.
Yeah, rank is 2. So what form you are getting? Finally, what is the form of the matrix that you are getting? Rank is 2. It is correct?
I'm upper triangular matrix.
You are getting it as upper triangle. So what are the elements?
No, sir, ma'am.
First row is 1, 2, 3, then 0, 1.
Okay, post it. Let me see so that others can also check out. Post the solution.
Ma'am, can you explain the minor method once again?
Minor method.
I'm a little confused.
Suppose you have this matrix. 5, 6, 7, 8, 9, 10, 11, 12. Minors are actually the sub-matrix that you are getting from the given big matrix. So this is the given matrix.
Yes, ma'am.
Okay, so minor will be the sub-portion. So you can take this as a minor. Determinant, so that you can get the determinant. For determinant, what you need? There is one property for the determinant. The matrix should be
Square matrix.
Square.
yes, the matrix should be a square matrix. So you have to choose one sub-square matrix from the given matrix that will form a determinant, that will form a minor. And that minor should be not equal to 0 to get the rank. So over here the square matrix 3 by 3, so this is one minor. So you can get multiple of minors. So this is one minor. And again, if you take this element, this is again another form of minor. What you can do, you can again combine these two elements. You can take this and you can take this. So this is again another form of minor. Got it? So in any other way that you can get a submatrix, those are the minors. So getting the submatrix from a given matrix, if it is a big matrix, it is very difficult and it is very time consuming. You will get, but it is very time consuming. You may miss one matrix whose value will be not equal to 0. Got the answer?
Got it.
And again, if you have a submatrix that is 2 by 2 matrix, so this will also be a 2 by 2 minor of the given matrix. So any submatrix of the given matrix are called the minor of the matrix. That is why I'm saying not to proceed with that minor technique. Post the solution.
There's one in the chat, ma'am.
Okay. Can you reduce further? Can you reduce this further?
Yes, ma'am. Yes, ma'am. I have reduced. In next page, I will.
Okay. Because this may not give a direct, clear answer. Okay, you have done it. So this way you have to proceed and you can get some form. So form I have explained you in which form you have to reach. You have to reach the form like this, either in normal form or in upper or lower triangular form. So you can have the element like this, 1, 0, 0, 0. If it is a 2, so over here you can say that it is a rank is 1. Okay, or you can have 1, 1, 0, 0, 0, 0, 0, 0, 0. Sorry. This form. So this is actually called I2, which I gave you in the definition. Either you can have it in this form. So this form you can easily get it. If you have some element, you can divide it with that element. Because if you divide, like if you have 2 over here.
I stands for identity matrix.
Yes,
right?
identity matrix. That is why I am written.
Identity matrix is 1,
But
0,
identity
0, 1.
matrix, yes, ma'am. Diagonal.
Sorry, yeah, diagonal. It will be diagonal one.
Ma'am, you are not audible.
And then find the rank of the matrix. Anybody having any doubt over here regarding the rank of the matrix, you can ask.
Ma'am, the previous question, what was the answer?
2. Rank of the matrix will be 2. So by which way method you are doing it?
Ma'am, fourth row, third element is 0 or 6?
It is 6 and this is 0.
Ma'am, please make everyone an attendee.
Ma'am, is the answer 3?
Yes, answer is 3. So what form you have converted to?
Euclidean form.
Okay. So you posted?
No, I solved it in just one matrix. Very rough.
So there are examples of here also in the book. You can just go through it. There are some row operation going on. See over here you can see that this last row all the elements are 0. And over here you see you get an I2 form matrix. Okay, so the rank is over here too. So this also I have taught row reduced echelon form. It will be of this form. Anybody else post your solution? Done?
I think I posted a solution in the general chat of the team.
Let me see. Yes, okay. But this is not the normal form.
Yes,
Yeah, this is actually
the upper triangular form.
Yeah, it is upper triangle.
We have to convert it to normal form.
No, any form. If it is mentioned in the book, like if you get MCQ, find the rank, then any form you can use.
Yeah, because
As per
normal
your
form is a bit
convenience.
lengthy.
Any form you can use, and if you are given a very small matrix, then you can use that first condition that take the minor and then or take the determinant. If a very small matrix is given to you. If you are having a big matrix, it is better you use the transformation.
I have also posted below that text.
Okay, so I think all of you all have understood what is rank.
Yes.
If you have any doubt, you can ask. you change the rows and column, will there be effective rank of the matrix? If you interchange any row or column, will there be any effect in the rank of the matrix?
No.
No, ma'am.
Why?
Equivalent to taking transpose.
Why?
I mean, when
Determinant value doesn't change.
we can
Yes.
take the transpose of matrix.
The transpose, if you take the transpose of the matrix also, that there will be no change in rank. Okay. Because the elements are the same. When you apply, take the determinant or this, whether you take the transpose or you don't take the transpose, the value that you are getting is the same. So the rank, there will be no effect in rank. So proof of these properties are not needed. You can just remember the properties so that you can solve. Okay, take another matrix. Okay, you convert this matrix to normal form.
Yes, ma'am.
Convert this to normal form.
What do you mean when you say convert it to the normal form?
I just said over here, have you noted down whatever I was explaining?
Yes, ma'am.
So this is the normal form. That means you will get some. What sum? Sum matrix which will be in an identity, matrix. Means some portion of the matrix which will be in identity matrix form. Or you can have like this, or you can have the identity matrix like this with other element 0. If it is a 3x4 matrix or something. So that is the normal form.
Is the rank 2?
Rank is 2, yes. Rank is 2. What's the solution?
Ma'am,
yes.
that question is 1, 1, 2, 1, 2, 3, 1, right? Or the previous one?
No, this one, not the previous. That was the previous problem. This one.
Okay.
Rank is 2.
Yeah, but this you have to reduce further because see, obviously this element, it is not in the structure of normal form because see, this element is not 0.
And the upper part was.
This upper part is identity, it is fine, but the remaining element you have to make it 0. So what you can do, you can subtract the third row with the second row. Sorry, you can add the third row with the first row. Yeah, now it is correct. So this is I2, identity matrix of order 2, and the other elements are 0. Okay, we shall meet again in the next class.